Hi everyone, in this video today I'm going to be going through the derivatives of exponential functions, and in particular functions that have e as the base on that exponential function. So you can see some graphs here of some basic exponential functions, 2 to the x and 5 to the x and 1.2 to the x, and the other side if we have fractions instead for the base. We've done some previous work that's talked about a particular exponential function that we're really interested in, that is 2.71 etc. to the power of x, and we call that y equals e to the power of x, and we know that that's a really important number in this context because the derivative is itself. So at every y value on the curve here, the slope of the curve is the same as the y value. So at y equals 1, for example, if we drew a slope here, the slope would be 1. When y is equal to 2, if we went across to this curve, you'd see that the slope was 2. Okay, so it's got those interesting features that the derivative of the curve is the same function. So let's do this problem now, which is a basic calculus problem, but we're going to use that function e to the x, the exact equation of the tangent at the point 2e squared, at the point where on the curve where y equals e to the x. So we need the derivative here. We're talking about the tangents and slopes, so the derivative is e to the power of x. Now to find the equation of a line, we need two things. We need a point on the curve, which we have, and we need the slope of the curve. So the slope of the curve when x equals 2 is e to the power of 2. So therefore the equation of the line is y equals mx plus c. And you might have done this a different way with y minus y1 equals mx minus x1. So if you use that method over there, that's fine. I'm going to use this one here on the left. So the y value is e squared. The gradient m is e squared. The x value is 2 and plus c. So that tells me that c is e squared minus 2e squared, which is negative e squared. So the exact equation of the tangent is y equals e squared x plus c minus e squared. There we go, that's the exact equation. Very important equation here, dealing with the chain rule when we start to differentiate functions that aren't just e to the power of x, but e to the power of a function of x. So we could use the chain rule if we wanted to do this. So let's say if we had y equals e to the x squared, let's say. All right, we could do a little bit of chain rule here and say u is equal to x squared, so du dx is equal to 2x. Okay, the derivative of that function u with respect to x is 2x. So now our original function is y equals e to the power of u. We've kind of made this replacement here where x squared is the same as u. Well, now we know dy du, we know the derivative of that function with respect to u is just e to the power of u. The derivative of e to the anything is just itself. Okay, but what we want is dy dx. So this is where the chain rule comes in. Dy dx, we're going to say, is dy du times du dx. Okay, and you can see how those could cancel these derivatives behaving like fractions, and we end up with dy dx there. Okay, I'm not going to do any cancelling like that, of course. So dy du is e to the power of u, and du dx we found up here was 2x. So remembering, of course, that u was x squared, we get e to the x squared times 2x. Okay, so I've just done one example there, but hopefully you can see that this formula here is valid, that when you have e to the f of x by the chain rule, the answer is just e to the f of x. So you write down your original function you were given and multiply it by the derivative of the power. So let's do these basic examples here. So for a, find the derivatives of the following functions. 4x cubed is going to be 12x squared plus 5e to the x. The derivative of that is just 5e to the x. Okay, the derivative of e to the x is e to the x. We'll leave the 5 there. For b, y dash is e to the x cubed plus x minus 2, e to the x cubed plus x minus 2. The first part's easy. You just write down the exact same thing as the question, times by the derivative of that power. So 3x squared plus 1. That's it. That's the derivative. And then I'm just following exactly this rule here. Okay, what the derivative is going to look like. And C, we've got f of x is 3 plus e to the x to the 7. So using the chain rule again, we're going to bring the number down the front, leave that thing in the bracket exactly the same, subtract 1 from the power, and multiply by the derivative of what's inside there, which is just e to the x. Simple. And I could kind of tidy this up a bit and say 7 e to the x, 3 plus e to the x to the power of 6. There we go. There's the derivative of that one. Now, of course, we can apply the product rule and the quotient rule to these questions now. So the first one, we're going to be using the product rule. So I write it like this. The derivative is u dash v plus v dash u. That's my shorthand notation for the product rule. So in this case here, we're going to say u is x squared, that first function there, x squared, and v is e to the x. So u dash 2x, v dash e to the x. There we go. So the product rule says that the derivative dy dx is u dash times v plus v dash times u. There we go. Just do that very carefully and very formally, and you'll always get these right for the product rule. I'm going to go one step further here and make sure that I've taken out a common factor, so I can see that in both of those terms there, x is common and e to the x is common. So that leaves me with 2 plus x. Okay, that's the derivative. Now, why is that important? A lot of these questions are going to ask you things like, what is the coordinates of the stationary point on this curve? Now, if you just leave it in this format here, it's difficult to see when the derivative is equal to 0. But given the form that I've written it in like that, it's much easier to see the values of x where that equals 0. I can see, first of all, the x equals 0 would make that whole thing 0. So x equals 0 would be a turning point. There's no values of x where e to the x is equal to 0. If you think about the graph of e to the x going like that, never is that graph equal to 0. Never does it touch the x-axis. So there's no values of x that are going to help us there. And of course, x equals minus 2. Okay. Once we've got those x values, we could substitute back into the original curve. So if we have y equals x squared e to the x, we could then find the y values. We could then determine the nature of those stationary points, etc., etc. So we're doing the derivative here, but I also want to point out that it's good to factorize, and one of the questions that you will get is things like, what is the stationary points? Second question, y equals e to the 2x over x. That is going to need the quotient rule to solve. Okay, so I'm going to say that this function on the top is u, this function on the bottom is v. And again, do this really carefully. U is e to the 2x, v is x, so u dash is e to the 2x, the derivative of e to the 2x is e to the 2x, times by 2, the derivative of 2x. So 2 e to the 2x, and the derivative of x is just 1. Okay, cool. So the quotient rule says that the derivative, and I'm using shorthand here, this is really should be dy dx, u dash v minus v dash u over v squared. There again is my shorthand way of doing the quotient rule. It'll be on the formula sheet. So u dash times v minus v dash times u divided by v squared. There we go. That is the derivative. And again, I'm going to tidy this up. The top line, common to both of those is e to the 2x 2x minus 1 over x squared. And that's about as nice as we can get it, I think. And again, I could ask the question, what is the x value of the stationary points on this curve? There are none coming from this x value here. E to the 2x is never 0, but x equals a half will make that bracket 0. So x equals a half is the only stationary value on this curve.